All right, everyone, welcome back. We're going to look at some stuff with correlation today. So we've been talking about statistics. We're going to continue to talk about statistics a little bit. But what we're going to look at today is if we have two sets of data and we want to see if they're related to each other. So basically we're saying, does the one have an effect on the other? And if so, how much of an effect? How much of it can be attributed to the other thing? So we're going to look at, since it's bivariate data, or the fancy term for two variables worth of data, we're going to have basically an x and a y-axis going on, and we're just going to plot the points in a thing called a scatter plot. So here's an example of a couple different scatter plots that we have here. Now, what we're going to try to do is see, are these related to each other? Now, if you look at a scatter plot and you see a pattern to the points, then they're related to each other. We're going to be looking at linear relationships today. There are nonlinear relationships between data as well. But if we look at this set right here, do you notice the best thing that I could make to fit this data would be a line going through approximately right there. Now, since a line going through right about there is the best thing to fit this data, this is two sets of things that are linearly correlated. They're related to each other by a line. And do you notice in this one, whatever this is and whatever this is, as the one goes up, the other goes down. Since that's the case, they have this inverse relationship. As one increases, the other decreases. We call this thing a negative correlation. So those two things, whatever they would be, are negatively correlated. And this would be a fairly strong correlation because do you notice most of the points are pretty close to that line? And so that's a negative correlation and a negative fairly strong correlation. Now this scatter plot here, do you notice if I wanted to make the thing that fits this data the best, it would still be a line, but it would be a line trending up this way. Now if that's the case, this would be still correlated to each other, but this would be a positive correlation. Positive because as one variable increases, the other variable also increases. So this is a positive correlation between these two items. Now this one would be a little bit weaker. Do you notice all the stuff's a little bit closer to the line in this one? Still a line is the best, but the stuff's a little bit farther away. This would be a slightly weaker positive correlation. And then down here, we just have randomness. There's not a line that would fit this data the best, really. There's not another shape, so if we could see something where there'd be like a curve fitting the data the best, we'd say it's still related but not linearly related. These are just basically unrelated. So these are two things that have no relationship to each other, and so they would have no correlation. Now let's talk in terms of numbers real quick, what this means as far as correlation goes, because there's going to be a numerical value that represents how correlated things are. And that's what we call a correlation coefficient. It's R. So lowercase r is how we represent this. And R is always a number between -1 and +1. Now I wanted to preface this little thing I have right here by saying this is not a set rule. There is no set rule for what makes a correlation strong, moderate, and weak. It kind of depends on what you're studying a little bit, and so don't go and say well, Mr. Wiles said that this is strong because it's 0.52. This is just kind of a general idea, and so I wanted to say that before I kind of talked about these. Now, do you notice we have only things between -1 and +1 for R? The closer R is to +1 or -1, the stronger the relationship. The closer R is to 0, the weaker the relationship. So the positive and negative has absolutely nothing to do with the strength of the relationship. I always like to stress that because that's a really easy mistake to make. All the positive or negative tells you is it positive, so as one variable increases, does the other increase? Or is it negative, as one variable increases, the other decreases? The strength of it is how close it is to 1 or -1. So anything close to 0 is weak. So 0.1 has the same strength as -0.1. They're both a weak correlation. 0.9 has the same strength as -0.9. They're both a strong correlation. So that's why if you notice when I have these drawn here, I have absolute values around the r's. So if the absolute value of r is above 0.5, we're going to call it strong. And remember, that's kind of like a guideline. That's not an exact rule. Between 0.3 and 0.5, we're going to call it moderate. And if the absolute value of r is less than 0.3, we're going to call it weak. Now, depending on what you're studying, a weak correlation, even if it's somewhat correlated, could still be significant. It just depends on what you're studying. So let's say you were studying shoe size and GPA. You would expect those two things to be completely unrelated. So if you're studying shoe size and GPA and you get a correlation of 0.3, that's kind of a significant finding because you're saying, hey, these things are somewhat related. I wasn't expecting these to be related at all. And so it really kind of depends on what you're studying a little bit, whether that's a big deal or what the correlation coefficient needs to be to make it significant. So another thing that goes along with this correlation coefficient is the coefficient of determination, it's called. Or the way we find this, it's really related to r. It's just you take the correlation coefficient and you square it. R squared is what we call the percent of explained variability. So basically it tells you what percent of the one thing can be explained by the change in the other thing. So a sentence that goes along with this, going with the shoe size and GPA thing we were doing a minute ago, you could say 10% of the change in GPA can be explained by the change in shoe size. That would be a statement of explained variability. Now, it depends, the percentage number would change based on whatever r squared came out to, but that's what the sentence would sound like. Now, if you want to sound a little fancier, you can replace that change in word with variability. And so you'd say like 10% of the variability in GPA can be explained by the variability in shoe size. All right, and then our last idea for today, which this is something that you guys should be familiar with because we've talked about this already, is line of best fit or a least squares regression line or linear regression. All those are words for the same thing. It's the line that fits the data the best. Now, because it's a line, it's going to fit the y equals ax plus b, or some people say y equals mx plus b form. So this number right here is going to be the slope of the line. This number right here is going to be the y-intercept of the line. And that's going to tell us the line that fits the data the best. So it would be the equation of this line that I have drawn in that one, or this line that I have drawn in that one. So those are our three big things we're going to do today, is try to figure out correlation coefficient, coefficient of determination, line of best fit. So let's try to do this with an actual set of numbers now. So what I've got going on this is we're looking at a table of data that has to do with absences in the third 9 weeks related to GPA. Now, this data is completely made up, so don't be afraid that I took somebody's GPA and published it here. I made these numbers up. So here's our absences. Here's the corresponding GPAs. Now, that's important. I couldn't just jumble up this order because these represent like a participant in the survey. The person who had 2 absences had a GPA of 2.8. And so these two go together. And that's going to be important when you enter these in. Now, I wanted to mention this because I have the answers for all these up here. You're going to see how to compute these in part 2 of this video. There are longhand equations, but to be perfectly honest with you, nobody uses them anymore. Because why would you? So everybody uses technology to come up with these correlation coefficient, coefficient of determination, and this line of best fit. So we're going to cover how to do that on a graphing calculator in part 2. But what we found out here is the line of best fit is approximately y equals 0.14x plus 3.69. So what this means, if you put this into your calculator in this order, this is your x list and this is your y list. So what this tells you is an equation that represents or that relates absences to GPA, where absences is your x value and GPA is your y value. And so you could actually use this then to predict values that weren't in your survey. So for example, what if you wanted to know what should your GPA be according to this model if you missed 35 days of school in the 9 weeks? Which is probably going to be pretty bad, which makes sense. And so you put 35 in for x, see what you get back for y, that would be your GPA if you missed 35 days of school in the third 9 weeks. Now, little word of caution with doing that. Unless this is a perfect correlation, your results when you put in that number for X and get a number back for Y are a guess. They're not an actual prediction. You can't use cause and effect language unless this correlation coefficient comes out to be exactly 1 or -1, meaning it's a perfect correlation. Which in real life stuff, quite honestly, is probably never going to happen. So you can use it as a guess, as an educated guess, as a prediction, but you can't say this is going to happen. So this correlation coefficient on this particular set came out to -0.91. Now what that means is it's negative. That means as absences go up, GPA goes down. Just notice something I forgot here. This is actually a negative on that too because the slope of this is negative. So as GPA goes up, absences go down. So that makes sense. We would expect that to happen. Absences increasing would make your GPA go down. So that's a negative correlation. Now it's 0.9. That's really close to -1, which means we would call this a negative and strong correlation. Now, I really want to make sure you guys understand what this means and can interpret that as what that means in terms of these particular variables. So what that says is there's a negative strong correlation between absences and GPA, or in other words, we're pretty sure that as absences increase, GPA decreases. So that's kind of what that means. And then R squared, basically just squaring this number, we get 0.82. All right, and there's more decimals on all this. I just rounded them to the nearest 10, or the nearest hundredth. And so R squared is 0.82. Now here's what that means. We said R squared, or the coefficient of determination, that's called, tells us the percent of explained variability. So what this tells you, and this is a significant statistic, this is one that I feel like is a really helpful piece of information. This tells you what percent of the change in the one thing can be explained by the change in the other thing. So just making this a percentage, remember to make a decimal percentage, we just move the decimal 2 places to the right. So we could say this. We could say 82% of the change in GPA, or variability in GPA, if you like that word instead, can be explained by the change in absences. So we're saying 82% of the change in GPA can be explained by the change in absences. Now, that's pretty significant. So what you're saying is 82% of the change in your GPA can be explained by the change in how much you're absent from school. That would be a very significant finding. Now, like I said, I made up these statistics, so I can't say that this is actually the case. Although I have done some statistical studies on this and found that it is a fairly high percentage. Maybe not quite that high, but it is a fairly high percentage for absences and GPA as a result of that. So there's an example of how we can use this information, come up with the line of best fit. We can put values in there and make predictions, come up with the correlation for how well it fits the line. So in this case, it's a strong correlation because it's really close to -1, and so this fits the data very well. And so this is a negative strong correlation, which means as absences go up, GPA goes down. And then R squared, or coefficient of determination, is percent of explained variability. 82% in this case of the change in the one can be explained by the change in the other. So there's our important stats for bivariate data, for comparing two sets of data. So I thought I'd give you guys a little glimpse of how I spent part of my spring break, and an example of negative correlation as well. So as you guys can see, my kids are huge fans of Harry Potter, and also big fans of Legos. And so part of what we did over spring break was to reassemble all of these. When spring break started, this was actually just in a pile there in this tote. And so I don't know how many pieces of Legos this was, like 4,000 pieces or something insane like that. But the example of negative correlation would be this. As the number of parts in that bin decreased, my happiness level increased. And so when this was all done, I was very happy. When I started, I was not very happy because there was a lot of Legos to put together. So I just thought that was a fun example, a little glimpse into the life of boredom and that we now lead, and just a good example of negative correlation as well.